Hello everyone, welcome to Vigyan Bharat. This is our second lecture of the real analysis course, and the topic of today's lecture is finite, countable, and uncountable sets. If you are someone new who is watching this video directly, I suggest you to first watch our first lecture, lecture 1, and then continue this video. Okay, so let's begin with today's lecture. This is the part 1 of this title. Part 1 of this title, finite, countable, and uncountable sets. So today we'll be going to cover numerous topics, very interesting exercises in this lecture. So just I want to say that watch the video till the end. So let's quickly discuss the very first notion of a finite set. If you recall from our primary classes, we have been counting certain objects, like if you recall, whenever we were present in every day in our class, then the teacher used to count the number of students present. There is a certain roll number which is assigned to each and every student, and through which, when the teacher asks that whether this one or he or she is present, then the teacher asks that particular roll number. So the notion of finite set in our case is a very simple notion, but in order to define this precisely, we require some mathematical terminology of bijection. So before moving to that, let me just quickly read what we have defined for finite sets. Let I choose my small n belong to the set of natural number here. This n is a natural number, and I have taken a set S which comprise or consist of these n elements a1, a2 till an, where the subscript below a, that is 1, 2 till n, what the subscript telling us the position of that particular element in the set. And this notation, capital N subscript small n, this set comprise of the set of first n natural numbers. Okay, so this I have assumed. Now with this information, this set S is said to have n elements if there exists a bijection, from this set to this set. If I am able to define a bijection from n subscript small n to set S, then in that case I will say that my set S is finite. Okay, so in order to understand it precisely, let's move ahead with the notion of bijection. First, let us discuss what is bijection. Bijection is also known as, in some books the author use another term for this, is one-to-one correspondence. So don't get confused if you find one-to-one correspondence somewhere, it is same as bijection. So let's try to understand this. Suppose we have two sets S1 and S2. We have two sets S1 and S2. I define a map small f between them. Now this map is said to be bijection if it satisfies two conditions. That the first condition is this map has to be injective, that is 1, 1, and the second, the map has to be surjective, that is onto. So in general now, if f is a map from S1 to S2, then it is said to be bijection if it is 1, 1 and onto. We know 1, 1, that what it means basically. If I choose let a comma b be two elements from S1, and if I consider fa equals fb, and if this implies, after solving this implies my a equals b, if I have this one, then in this case I set f is 1, 1. An equivalent way of this is if I choose whenever two distinct elements, suppose again choose elements a and b which are distinct, and if this implies their image is also different, fa is not equal to fb, and this should hold whenever we choose a and b different. So whatever choices of a or a and b from the domain you are choosing, different elements, their images are also different. In that case, we say that such a map is 1, 1. The second f is said to be onto if for every element in the codomain there exists at least one element in the domain such that the map f maps that element of the domain to that element of the codomain. That what it means basically, that element of the codomain has a pre-image, has at least one pre-image in the domain. So in that case, f is said to be onto. These notions are very fundamental. They often we have studied whenever we studied the concept of functions. Okay, and of course, whenever I'm choosing such a map, then in this particular case, my both the sets has to be non-empty. If I'm able to find such a map between any two such non-empty sets, then in that particular case, I say that this map is a bijection between S1 and S2 in this particular case, or whatever sets we are having. Or this map is a one-to-one correspondence between them. Okay, so let's go back again to the starting notion from where we left. So here I said that S is said to have n elements if I'm able to define a bijection from S to the set of to the set n subscript n, which is nothing but a set of first n natural numbers. If I'm able to define a map between them, then in that particular case, this S is set to have n elements, and of course it's finite. Now this is the definition, proper mathematical definition of a finite set. A set is said to be finite if it is either empty or it has n elements, where some n is some fixed natural number. So if any set satisfy either of these properties, if it is either empty set or it has exactly n elements, then in that particular case we say that set is finite. Okay, now let's move ahead into the lecture. There is an important exercise which I asked you over here, that think of the map which I defined above, f from, here I'm defining from n to s. Is it possible for other way around also? Is it possible to define that bijection from, if suppose say I'm defining from A to B and I'm calling A is finite, and if that A has exactly a bijection to a set which contain exactly n elements, then is it possible to define the map other way around from B to A? So try to think it also. Answer me in the comment box. Yeah, that I have asked will still be a bijection. So try to think of some examples. Try to think it. If it's yes, then try to prove it through a reasoning, mathematical reasoning. And you find some counter example, then try to think it in that case also. If the map is bijection, then there's a good important remark before moving ahead, that S1 and S2 in this particular case are said to be equivalent. In this particular case, these two sets are said to be equivalent if there exists a bijection between them. And in this case, these two sets have the same cardinality, which is denoted by this, the name of the set within the absolute vertical bars. So again, be careful that this is the case of finite sets, whatever we have just discussed. Okay. Now, this is the second exercise in the lecture, which I asked you to prove that this S is this relation. You try to prove this is an equivalence relation. So what is the relation? You are defining a relation between these two sets S1 and S2. How it is defined? If you can find a bijection between them, then they are said to be related. So try to prove this is an equivalence relation. That is, it satisfies the property of reflexive, symmetric as well as transitive. So try to prove it. Now this third exercise, marked by star. By star I mean that it's an important exercise for you. If you do this, then definitely many of your concepts will be clear. So the third exercise says that you want to prove that the inverse of a bijection is again a bijection. To define a bijection from one set to another, try to define the inverse of the same map. Try to define the inverse map. Then you try to prove that the inverse map is again a bijection. So try to prove this result. If you have any queries related to this, drop me in the comment box or either in the Telegram group. Now let's move ahead to the notion of infinite sets. Notion of infinite sets. So we have defined what it means to be said to be finite. Now a set is said to be infinite if it is not finite, that it violates those conditions for finiteness. So in such a set is said to be infinite. So here are some particular examples which I have just noted down. So let's quickly go through them. The first example is of the set of natural numbers, which we denote by this bold capital N, and which consists of all these natural numbers starting from 1, 2, 3, 4 and so on. So this set is an infinite set. Then second example is, if you collect all the even integers and all the odd integers, then those two sets will again be infinite. The next set is the set of rational numbers. We have already also discussed this. This is the collection of all fractions of the form m by n, where our m and n are integers. M and n both are coming from this set, but there's a condition that the denominator has to be non-zero. So this set is again infinite set. Now, this is very important. Sorry. This set, the set of real numbers, is again an infinite set, which we denote by this open interval. And in set theoretic notation, we write it like this. So this is again an example of an infinite set. Try to construct more examples yourself. Try to construct. Now, here again a question I have asked you, right, in order to check your fundamentals. Is these two symbols which I have just denoted by minus infinity and infinity, are these real numbers? Yes or no? So try to again answer me in the comment box. Okay, so this we studied about the infinite set, the definition. Let's now move ahead to some interesting results based on both finite and infinite sets. Let's discuss the first result. What it says that if C is an infinite set and B is a finite set, C is an infinite set and B is a finite set, now you are taking the complement of B with respect to the set C. In the last lecture, if you remember, we defined the complement between two sets. So the complement of B related to the set C, that is, you are collecting all those elements which are in the set C but not in the set B. So if you find this set, now I have left as a space blank over here. The resultant set, this set, I'm asking this set whether will it be a finite set or be an infinite set. I ask you to pause the video here and try to think it once yourself. I hope you have given a thought to it. The answer is infinite. And it is quite obvious and straightforward that if we have an infinite set and B is a finite set, and we are now, what we are doing basically, we are just removing some elements, finite number of elements from an infinite set. So the resulting set is again going to be infinite. Okay. Now this second is a very important result, I would say, because whenever we'll be moving ahead in some good problems, then we will be able to use it. It's a very powerful result. So let's try to again understand this. Suppose that we have two sets S1 and S2, and how they're related, that S1 is a subset of S2. This satisfies that S1 is a subset of S2. You should remember what we mean by subsets again, as defined in the previous lecture. Subset basically mean that every element of S1 is also a member of S2. Then what it says, the first point of the result is, if S2 is a finite set, this one, if S2 is a finite set, then what the result says, then S1 will also be a finite set. The second point in this result is that if this set, this S1 is an infinite set, then its superset S2 will also going to be an infinite set. I'm skipping the proof of these because we're going to use them. Okay, so now let's move ahead to very important types of infinite sets. Broadly, we have divided the infinite sets in two categories. So what are those two categories? The first category is countable. The second category is uncountable. Fine. Now in the first category, we have two subcategories again. What are those subcategories? If you see here, the first is a finite set, and the second one, this is very important. This one is very important for us. Denumerable sets, which are also, some authors also call it countably infinite. So again, repeat, broadly there are two types of infinite sets, countable and uncountable. Countable is again further divided into two subcategories. So finite, we have already covered what we mean by finite set. It is either empty or it has exactly n elements. Now let's study what are denumerable sets or countably infinite sets. So denumerable, what it means by denumerable set, that you have an infinite set and what you want to enumerate each of its elements. What we are doing there, at one side you have this infinite set, at another side you have a set of natural numbers. Corresponding to each of natural numbers, you are assigning an element of this set. So what we are doing exactly, we are trying to again find a bijection. What I am trying to find, a bijection. Suppose the infinite set which I have, I denoted by capital S. By standard convention, we know that the set of natural numbers is denoted by capital N. If I am able to find a bijection between them, then in this case we say that my infinite set S is denumerable or countably infinite. Okay, so here is the definition. S is said to be denumerable if there exists a bijection, that is, if we can find a small f map from N onto S, which is bijection, that is injective is surjective. Then in that case, this infinite set S is said to be denumerable. Let's try to see this example again. Example over here. Let my E denotes the collection of all even natural numbers. What I have collected, all the even natural numbers, written as 2n, where my n is an element of set of natural numbers. And I have defined a map F from the set N to E. I have defined a map from the set N, that is the set of natural numbers, to the set of even integers. How I have defined? I am assigning my every natural number to corresponding to its twice natural number. That is, suppose I pick 1 from the set N, then if this F maps 1 to 2, if I pick my 2 from the set of natural numbers, then f of 2 is 2 times 2, that is 4. So let's see this something, what I'm doing, basically very simple. Here is your E, here is your N, this is your F, this is your infinite set which goes like this, here is like this. So what this F is doing, it picks one element from here, send it to here, 2 to 4, 3 to 6, and so on. This continues, this map continues like this. So we can easily verify that this F defined over here is a bijection. It is both 1 1 as well as 1 2. You use the definitions and try to prove it that it's a bijection. So if it's a bijection from N to E, then this my original set E is denumerable. Fine. Now I give you another exercise here, in this particular example, that try to find a bijection other way around, from E to N. Try to find it. Okay, and prove it, it's again a bijection. So my is denumerable or countably infinite. Now this is a very important exercise number 4 of the lecture. Now I'm collecting all my odd natural numbers this time and storing in a set which I'm calling by D. So let here, if you see that this D denotes the set of all odd natural numbers. So D comprises of basically this 1, 3, 5 and so on. Its general element will be 2 and minus 1. 1 less than an even natural number, okay? So try to prove that this try to construct a map from the set of odd natural numbers to the set of natural numbers, or other way around, that it is a bijection. Prove it. Okay, a good exercise for you. Now, this is a very powerful result, I would say, that if you take two denumerable sets and if you take the union of any two denumerable sets, but there's a condition, this should hold, that they are disjoint. But what you want, what is the requirement of this result, that whatever two sets I am having, two disjoint sets I am having, and of course they are denumerable, then their union, if I take the union of those two sets, then it will again going to be a denumerable set. Okay, so what it says, that if I have a set A which is defined over here, A1, A2 and so on, if I have another set B which is defined as B1, B2 and so on, where A intersection B is empty, that is they are disjoint, then if I take the union A union B, then this resulting set is again going to be enumerable. That is, we can enumerate the elements of the union. Union is a new set. So if I take the union of these two sets, then again the elements of that set are enumerable. And how we can enumerate them? Enumerate means simply that I'm able to count them, or I'm able to you can think it in a very another simple way, that corresponding to every element of the set there is a natural number. So what I can do, I can stamp a natural number to every element of the from the set, this union. I can assign a natural number to each and every element. So if such a condition is set, if I'm in such a scenario, then the resulting set is denumerable, or we can enumerate the elements. Okay, so what is the rule here? If you see how I can enumerate the element of the union, in the first position there exists a natural number 1 corresponding to this. Now this is corresponding to the second natural number, this is corresponding to the third natural number. So in this way I'm able to assign a bijection from A union B to N. Okay, so now using this powerful result, if you see these two things, the first thing is, we have proved above that the set E of even natural numbers is denumerable. The set D of odd natural numbers is denumerable. Both are disjoint. If you can verify the set of even natural numbers and set of odd natural numbers, both are mutually disjoint. So if I take their union using this result, then the resulting set of union is nothing but a set of natural numbers. So their union is denumerable. Their union is denumerable, which is just I have mentioned here. This is the observation which we found from the result. Okay, so it was a good result. So now, before concluding today's video, there are some good important exercises at the end. So let's quickly go through them so that you can ask yourself whether whatever theory we have covered, you are able to understand something out of that or not. So this first exercise is a very important exercise, because if you are able to prove the first exercise, then the idea which we use in this will later going to be help, and will be moving ahead with the Cartesian product of finite Cartesian product of denumerable sets, denumerable, and even generalizing it also. right? To prove the first exercise that the set Z of all integers is enumerable. Try to prove this. Second exercise is a very elementary, but you should do that. But it says that if I have a set D which consists of two elements, 3 and 5, I also have a set T which consists of three elements, small p, t, and small v. Then the first question which you should do, which you're asked, that determine the number of injective maps from the set D to the set T. That is, injective means number of 1-1 functions. Number of functions from D to T, different indeed, different, how many different 1-1 maps you can define. So try to find this answer. In the second part, you have to answer the number of surjective, or surjective means onto maps from the codomain to the domain, that is T to D. Okay, I have written into D into D, it is same as D to D, so don't get confused by that word. Okay, now at the very end, there's a last exercise for today, third exercise, but it says that is it possible to define a bijection from the set n of natural numbers to a proper subset of itself. If you recall the last video, we have already covered what we mean by proper subset. Proper means that we have two sets A and B, then A is said to be proper subset of the set B if there exists an element in the set B which is not in the set A. Let me quickly define for you before concluding the video, that if, like this, I denote A is a proper subset of B if there exists some x in B such that x is not a member of the element A, of the set A. Okay, so in that case, we say that my set A is a proper subset of set B. So try to complete all these exercises and go again through all this theory what we have covered. And this was the part 1 of today's topic, that is finite, countable, and uncountable set. This was the part 1. We'll be moving ahead into the part 2 in the next lecture by continuing again the notion of countable sets, discussing some of very good important result of countable sets, and theorems, also some good theorems and problems based on them. So we'll go into that, and at the end, before concluding, just I want to say that if you like this video and find it to be useful, then do give a like, and do subscribe to the channel if you are someone new, and do share about the initiative which we are doing to among your friends, so that they can also get benefited from it. So thank you so much for watching, and we'll be moving ahead in the next lecture with the countable sets. So thank you so much.